Okay, in this chapter, chapter 4, we're going to look at the distribution of the OLS estimator, and we're going to derive out the results under an assumption of non-stochastic regressors. Okay, this means that we're going to assume that the x's are not random. So it kind of limits the application of the results because we're saying for this sample, these are the results derived. And this is the way the original OLS estimator was first analyzed, and then later there was some more work on generalizing it to allow for any random sample X. So later on we will eventually generalize it also. The only reason for doing it this way is that the results are a little bit simpler to derive, and then doing it the other way where we allow for random X's, we basically get the same formula. Okay, so it's mainly just for simplicity because I think it's easier to understand it first this way. Okay, so the assumptions of the OLS estimator. So this is the model we're looking at. Okay, this really I equals 1 to n. We're going to assume that the mean of the residuals is 0. The variance is homoskedastic, so it doesn't have an I subscript. You know, it's the same across all observations. There's no covariance across observations I and j. Another way to write this is that the variance of epsilon vector is sigma squared I. Let's see. Yeah, and then we're going to assume for now that the epsilon is normally distributed. Later on, we're going to relax this assumption because actually the OLS model is valid even if epsilon is not normal, because you can get normality applying a central limit theorem. But for now, we'll just assume the epsilon is normal, which is kind of the way the model was originally derived, like in the 1950s. So we'll start with a simplifying assumption. Okay, and then we'll assume X prime X matrix is invertible. So that basically means that you don't have collinearity, that none of the regressors are linear combinations of other regressors. Okay, so so to see, that the variance of epsilon is equal to sigma squared I, first let's write out what is the variance of epsilon. Okay, so if the mean is 0, then it's just going to be expectation of epsilon prime. So epsilon here is n by 1, and epsilon prime is 1 by n. Okay, so epsilon prime is n by n, so this is a big matrix, okay? So if we take the expectations here, you can see on the diagonals, it'll all be sigma, or sigma squared, and then on the off diagonals, it'll all be 0, right? Okay, so that this is just showing that the variance has this form. Let's first show unbiasedness of the OLS estimator. So if you take the expectation here, so plugging in for y, because we want to relate it to beta, okay, so we have to get beta in there somehow. So let's plug in for y. Now we're going to treat the x as if it's constant, okay, that's what the non-stochastic lets us do. Okay, so this x prime x inverse x prime x is going to be the identity matrix. Then here we have x prime x inverse x prime epsilon. And if the x's are constant, you can bring the expectation right in there, pull the x's outside the expectation because they're not random. And then the mean of this is 0. Okay, so that means that the estimator is unbiased. Okay, so now let's look at the variance of the OLS estimator. Okay, so beta hat is a random variable, or it depends on things that are random. So remember, beta hat is x prime x inverse x prime y. Even if x is constant, y is random because y also depends on epsilon, and we're assuming the epsilon is random. So beta hat is going to have a variance, okay, because it's random. It depends on things that are random. Okay, so I'm sure you learned in your earlier statistics classes, this is the formula for random variable. Okay, so now we basically do the same thing except z is a vector. So if we have z that's an n by 1 vector, this would be the formula for the variance. Okay, which, if you multiply these things out, you can also write in this way. So instead of squaring it, you basically take this and then this prime. Okay, so now let's look at the variance of beta hat OLS. Okay, so we put in here beta hat OLS, here's the mean. We just showed that the mean is equal to beta. Okay, and then remember we had this formula here. Well, it's basically here that beta hat OLS is equal to beta plus this here. So we're going to put this in here. Okay, now this is transpose, so we can use the property of transpose that quantity AB transpose is equal to B transpose A transpose. So this actually, we reverse the orders. You get epsilon transpose X, X prime X inverse. This is actually transpose here, except it's a symmetric matrix, so transpose doesn't actually do anything. Okay, now we'll move the expectation inside because the X is assumed non-random. And then we can use our earlier result that E of epsilon prime is equal to sigma squared I. Okay, and sigma squared is just a number. You can pull it outside. So we've got X prime X inverse. So one of these will cancel and you're left with this. All right. So that's the formula that you would use to get the standard errors for the OLS estimator. The only thing is you'll have to, to implement this, we need an estimator for the sigma squared. Okay, later on we're going to actually show that the estimator that we use for this is an unbiased estimator. So we're going to study this estimator for sigma squared a little bit later. Okay, so now let's look at the asymptotic distribution for the OLS estimator. So we looked at the variance, we looked at the mean. Okay, now we're going to look at the asymptotic distribution. And we're going to use here that epsilon is normally distributed. And to show this, we need to first just understand some general properties of normal random variables, okay? So if V, well, actually random vectors. So if V is a vector that's normally distributed with some mean and some variance, then if we pre-multiply V by some matrix, okay, that's going to be normally distributed with the mean AB and the variance A sigma A prime. Okay, so you can think of this a little bit like I'm sure you did in statistics where you pre-multiplied by some constant, remember? And so the variance of like A times X is A squared variance of X. Well, instead of the A squared, you just pre-multiply by A and post-multiply by A prime. Okay. All right, and then if we pre-multiply by root n, then the mean would be multiplied by that, and the variance is root n squared. So it'll be multiplied by n. So let's apply these properties now to analyze the distribution of the OLS estimator. Okay. So we're assuming this is normally distributed, and this X prime X inverse X prime, this is basically playing the role of A. This is like the A on this previous slide. Okay, so we're going to have this as the A, and then we have that same A prime. Okay, and this is the thing which is like the V on the previous slide. This is normally distributed, with mean 0 and variance sigma squared I. And then all this stuff is like the A matrix. Okay, and so some of this is going to cancel, and you get beta hat OLS normally distributed, mean 0, with this variance. Okay, We drop the transpose here because x prime x inverse is a symmetric matrix. This is a k by k matrix, and it's always symmetric. Okay, so remember we talked about that you would like the estimator to have the property that the variance goes to 0 as n gets large. So does this happen for this here? Well, if you write x prime x in this summation format, you can see that this is actually getting large. Like as n gets large, you're adding more and more terms. Okay, so this is actually getting large. And the inverse is a little bit like 1 over, so like if it were just 1 by 1, the inverse would be 1 over, okay? But this term inside is actually getting big, and the inverse is then getting small, okay? So the variance is actually going to 0 as the n gets large, and meaning that the estimator is more and more has more, well, our estimate has more and more precision because it has a smaller variance as the sample size gets large. Okay. I mean, later on we're going to look at, how to prove something's consistent. And one of the ways to prove it first is to show that the variance goes to 0. Okay, now how do things change if we allow for heteroskedasticity? So remember, heteroskedasticity is saying that the variance of the error might depend on I. Okay, and one situation where this often happens is if we're running regressions where the individual observations are means, like state means, classroom means, some sort of means that usually leads to heteroskedasticity. All right, and so in this case, the variance of epsilon prime has this form. So it's not sigma squared I. It has this more general form. I mean, actually, I guess we don't need this expectation. This, just ignore this. It's just this matrix without the expectation. Expectation doesn't do anything because these are numbers, okay? All right, so in this case, the variance expression takes a more general form, right? Because if you go back to here, let's see. To here, you won't have the sigma squared I. You have an omega here. So you can't get rid of the omega. Okay, so you see it has this more general form. Okay, but we can estimate this x prime omega x by this. I mean, there are actually papers proposing to do this, so it may not be immediately obvious, but this expression actually imposes the zeros, because we know the omega matrix, all the off-diagonal element are 0, and so when I'm writing this way, I'm imposing those zeros. Okay, but this would be the variance formula with heteroskedastic errors. And this formula is called the robust standard error formula. So some packages, like I think Stata does this, where you just have to add the option robust and it reports these standard errors. And the nice thing about robust standard errors is they're valid even if you have homoskedasticity. Okay. Okay, so that's the last slide. All right, so just like to recap a little bit, this chapter we're looking at non-stochastic regressors. Later on we'll derive similar results where x's are allowed to be random. I mean, we first have to, cover some theorems and asymptotics that allow us to do that. So this is kind of like a preliminary version where we impose some stronger assumptions on the model that x is not random and that the epsilon is normal, and then later we'll relax those assumptions and derive similar results under more general conditions, okay? But we showed unbiasedness, we showed what the variance is, we showed asymptotic normality, right, using these results about quadratic forms. So we will be working a lot with quadratic forms when we do testing. Okay, and then, oh, this slide I think we skipped, maybe, for some reason. So here, the sigma squared, this is the estimator that's normally used. Okay, where k is the number of parameters being estimated, and epsilon I hat are the fitted residuals from the regression. Okay, later in chapter 7, we'll show that this is an unbiased estimator. Okay, and then we looked how the formula changes a bit when we have heteroskedasticity.